Hello, and welcome back, Focus Learners. Today, we're taking what a lot of people consider a notoriously dry subject, calculus, and we are completely transforming it. We're turning it into an empowering, highly visual toolkit. We're exploring the calculus of motion, and we're going to unlock the foundational rules of differentiation. These rules are literally the mathematical keys to measuring dynamic, continuous change across the entire universe.
Before we get into the heavy math, we kind of need to set the philosophical stage here. Think about the difference between a static world and a dynamic world. In a static world, math basically just tells us where something is at a specific given moment. It's a snapshot, right? A frozen frame. But actually, scratch that, we don't live in a frozen universe. In our totally dynamic world, we need to know exactly where things are going and exactly how fast they're getting there. We need a reliable way to measure the flow of time, of motion, and of growth.
Okay, let's dive into this. Differentiation is basically our precision toolkit for analyzing continuous change in these dynamic systems. Imagine a bright blue tangent line, just barely grazing a curved white path. That single line represents the exact trajectory and momentum of our system at one isolated microsecond. Calculus is the tool that lets us calculate the slope of that exact line.
And just to show you that this seemingly dense topic is actually highly organized, here's our quick roadmap. We'll start by capturing the basic rate of change, build our way up through algebraic and transcendental tools, handle products and quotients, unpack nested systems, and finally, synthesize it all into the differentiation matrix.
So let's jump right into Section 1, capturing the rate of change. This is the absolute core foundation we need before we get into the actual rules. Think of the derivative as, essentially, a mathematical magnifying glass focused purely on change. The original state of our system might be described by a standard function, like y equals f of x. But finding the rate of change means we have to take the derivative. You'll usually see it written out as f prime of x or dy over dx or maybe d over dx of our function. But honestly, regardless of the notation, they all mean the exact same thing. We're applying our magnifying glass to capture the precise rate at which our function is changing right now.
With that concept in our back pocket, we are ready for Section 2, the power progression.
We're going to look at three core algebraic rules to get us started: the constant rule, the linear rule, and the absolutely crucial power rule. These form the base we're going to use to build up progressive complexity.
First up, the constant rule. A constant is just a flat line, like say y equals -5. Flat lines never change, right? So their derivative is simply 0. It's the most boring rule for sure, but totally important. Next is the linear rule. If we have constant growth, like y equals 4x, it yields a constant rate, so the derivative is just that slope, which is 4. But then we hit the power rule, Rule 3. This is the real engine of basic calculus. If you have x to the power of n, you simply multiply by the power and reduce the power by 1. So an equation like y equals 2x cubed simply becomes dy over dx equals 6x squared. You pull that 3 down, multiply it by the 2, and drop the exponent to a 2. It's a beautifully mechanical multiply and reduce motion.
Let's move to and see how this builds when we're dealing with sums and differences. That's Rule 6 and 7. The good news here, you don't need some complicated new mathematical structure. When functions are added or subtracted, you just distribute the operation and differentiate each piece totally independently. The rate of change of the whole is really just the sum of the rates of its parts. So taking the derivative of 2x to the 5/3 minus x to the 8/3 is literally as easy as applying that power rule we just learned to each term separately.
All right, now that we've mastered basic polynomials, we need tools for more complex, naturally occurring curves. Welcome to Section 3, the transcendental tools. Rules 4 and 5 are just fascinating. The exponential rule uses the mathematical constant e to describe natural compounding growth. And what's absolutely amazing here is its self-replicating nature. The derivative of e to the power of u is, well, it's simply e to the power of u again times the derivative of that u exponent. It literally copies itself. Then we have the natural logarithm rule. The derivative of natural log of u is 1 over u times the derivative of u. Together, these two tools give us the extreme precision to track runaway growth curves and flattening saturation curves perfectly.
Okay, so that covers individual functions and simple addition. But what happens when things get messy? Let's open the next compartment in Section 4, Products and Quotients.
Ask yourself this: if two independent dynamic systems are interacting, say they're multiplying together or dividing each other, how on earth do you measure their combined rate of change? Because you can't just multiply their independent rates, no way. That would be like trying to figure out the speed of a car by multiplying the spin of the engine by the rotation of the tires. It just doesn't work.
And this brilliantly illustrates our solution, the product rule. Think of two multiplying functions as interlocking gears. When they multiply, their rates of change directly interact. You have to account for how one changes while the other remains constant. The rule handles this super clearly. The derivative is the first function times the derivative of the second, plus the second function times the derivative of the first.
Let's actually look at concrete proof that these abstract rules have highly methodical, step-by-step applications. Say we are combining rules to differentiate an equation with two terms. The second term is 10x cubed times the natural log of x. Because those two x variables are multiplying, we absolutely must use the product rule. We identify our u as 10x cubed and our v as natural log of x. We find their individual derivatives, and then we cross-multiply them according to our formula, adding them together. Finally, we just synthesize everything back into one clean final derivative equation. It is pure step-by-step logic.
Now, what's really interesting about this slide is that division changes the game entirely. This is Rule 9, the quotient rule, and we use it for structural ratios. Unlike addition or multiplication, division is not flexible at all. Because our formula has a subtraction sign sitting right there in the numerator, the order of operations strictly matters here. Think of it structurally like a 3D block. It is the bottom times the derivative of the top, minus the top times the derivative of the bottom, all divided by the bottom squared. If you get that order wrong, your whole calculation literally reverses direction.
All right, we have arrived at the final and definitely most intricate category of our differentiation toolkit. Section 5, Unpacking Nested Systems.
This is Rule 10, the chain rule. We use this for composite functions, which is basically a function placed inside another function. Think of it like a box inside a box. The golden rule here is that you must differentiate the outside layer first, leaving the inside completely untouched, and only then do you multiply it by the derivative of the inside layer.
To make sure you feel totally empowered rather than overwhelmed by the chain rule, always follow this simple mechanical three-step procedure. Step 1, differentiate the outside function while completely ignoring the inside. Step 2, differentiate the inside function all on its own. Step 3, combine them by multiplying the results together. So let's see this in action.
Here's a classic chain rule problem, finding the derivative of the square root of 5z minus 8. First off, we rewrite that square root as an exponent, a power of 1/2. Now we can clearly see our nested boxes. The outside function is the something to the power of 1/2, and the inside function is the 5z minus 8. Step 1. Apply the power rule to the outside, dropping that 1/2 down. Notice the inside stays exactly the same. Step 2. Now we differentiate the inside, which simply gives us 5. Step 3. We multiply them together, giving us our final, beautifully unpacked derivative.
Wow, okay, we've covered immense ground today. It is time to bring all of these distinct tools into a single cohesive framework in our final section, the differentiation matrix.
So the crucial point is that you really don't need to hold a chaotic jumble of math in your head. It all organizes perfectly into a single unified reference guide for continuous change. From your core algebraic rules up to your transcendental curves, straight through to the rules for interacting systems, this matrix is your fully loaded precision toolkit.
Which leaves us with one final thought. The universe is not some static picture. It is an incredibly dynamic, constantly shifting system of variables. And now that you have the matrix and you truly understand the foundational rules of differentiation, how are you going to use these tools to measure the change happening in your own world? Whether it's economics, physics, engineering, the magnifying glass is now in your hands. Keep learning, keep calculating, and I'll see you in the next explainer.